Hello. All right, welcome back. Today we will start a new uh, chapter. It's called basically the advanced version for graph algorithms. So in a previous chapter or previous lecture, we covered what we call the elementary algorithms, um, from basic search algorithms like breadth first search and depth first search. So it's basically the purpose of those search algorithms is to go through all the vertices in an efficient way without without traveling over the same edges for multiple times. And Also there are two algorithms that is based on the depth first search DFS, which is the topological sort, and the strongly connected components algorithms. And these algorithms, they primarily focus on the connectivity of the between the vertices. Okay, so no matter directed or undirected, the edges are not weighted, and how the relative distance between the vertices are measured based on the number of edges. Like the BFS will annotate each vertex with an integer number, which shows how far away the current vertex is from the source vertex. And these matrices are, those distance matrices are based on the number, the count of edges, rather than the weight of the edges. But we know that in a more advanced version of a graph, the the edges, they can have a weight. Like those weights can be integer numbers or float numbers that indicates the cost to connect or the cost to travel between the two connecting vertices. So the graph algorithms, the advanced algorithms that we will cover in this chapter basically rely on the weights of the edges, and they are more focused on towards counting the weights, including the weights of the edges in determining the topological structure of the graphs. So there are basically two types of problems that we will cover. The first one is called minimum spanning trees problem. And the second one is the single source shortest path. So these two types of algorithms, they are heavily focused on the weights and on the weight-based distances. And for each type of the problems, we will have multiple algorithms that can be used to solve them. And we will, so for basically for each subproblems, there will be quite a bit of content. And hopefully in this week, we will cover the minimum spanning trees problem, the first type of problem. And this is quite a problem that has a lot of inspirations from real world problems. One of the most important and the most famous example is the circuit wiring problem. So imagine on this electronic circuits, and there's those metal pins, right? And the designer need to make those some of those pins electronically equivalent by wiring them together, okay? So that they're at the same voltage level, right? So the task is to interconnect, say there you've got n pins and you need to interconnect those pins. But when you do this task, there's some considerations, there's some cost issues you need to take into consideration. Like you will pay for the amount of wire that will be used, right? So often speaking, the one that uses the least amount of wires is usually the most desirable, right? So this so if you look at this example, this is not an ideal example because the red circles in it, you can consider those red circles as the pins, and the straight lines connecting those red circles are the wires. And not all of these wires are not necessary, because when these two, for example, when these two pins are already connected to each other, then this vertical wire is not necessary, right? Because it can be these three, they are already interconnected through those two wires. So there's a lot of very flexible, oh, sorry, cancel the screen share. A lot of the issues factors you need to consider, right? You don't want to leave one pin out, but also you want to save the amount of wires. So in the second example, it saves much less, it uses much less wire, but the purpose is still satisfied. All the pins, they are interconnected. That means I can go from any node, I can go from any vertex to any other vertex on this circuit graph. But still, this one can be further optimized, be further improved. For example, if I cancel these relatively long vertices, right? Replace these long vertices with the shorter vertices here, right? With the shorter vertices, so that the total length of the wires can be further saved. So that is basically what the type of problem that's the minimum spanning tree problem is describing. Okay. So formally speaking, a minimum spanning trees is defined on a connected, undirected graph. So by the term connected, we mean that there is always a path between every pair of vertices. So there's no, in another language, there's no unreachable vertices. There's no isolated vertices. Okay, so it's always we can always reach to any vertex given any source vertex. And if we describe the circuits with a graph, then the pins, all the pins on the circuits will be the vertices, the set of vertices. And the connections between those pins will be described by the set of edges. Okay, so these circuits can be described by a graph model. So more importantly, for each edge from vertex U to V in a graph, we will have a weight function, W of the two vertices on the two ends, U and V. We'll use the weight function to specify the cost to connect the pin U and the pin V. Okay, so this cost can be the length of the wire, or it can be the money, and in the different settings, this can be the traveling time and so on, right? So the goal is to basically find a note that here we use the term acyclic subset of the edges. Okay, so this acyclic subset T is a subset of the edges that connects all the vertices. Okay, and we want the total weight the total weights of these subsets of edges should be minimized. Okay, so this is the formally defined goal. Okay, so this time the subset T is not a subset of the vertices, but it is the subset of the edges. We need to select only a subset of the edges, and those edges should connect all the vertices. And meanwhile, the total weight should be minimized. So it is a very typical optimization problem, but under a constraint, right? We need to optimize the total summation of the weights, but we also need to keep in mind that this constraint needs to satisfy. We need to select all the, we need to make sure that all the vertices are connected. Okay, we should not left behind any vertex. All right, so let's look at a graph, simple graph demonstration here. We have this time the letters as the vertices and the integer numbers refer to indicates the weights for each edge. Okay, so because the subset, the resulting subset T is acyclic, and it also connects to all vertices. So it's actually a tree structure, right? If you like lift any, use any vertex as a root node and then lift up all the edges, they will hang over there like just like a tree structure, right? So we can call this the results of solving the minimum spanning tree as a spanning tree, because this subset, the T, makes sure that all the vertices are reachable, are connected. So that means we actually spans across the whole graph. Okay, and the problem itself is called by the minimum spanning tree problem. Okay, so one technical detail we may need to pay attention is that the minimum spanning tree is actually short for the minimum weight spanning tree. Okay, we are minimizing the weight, the total weights of the edges, but not the number of edges. Okay, so this is a quite important difference, because all the spanning trees, the number of edges is fixed. Okay, because we are spanning over the graph and we need to connect all the V vertices, and that makes sure that the number of edges is V minus 1. Okay, so there's nothing to be optimized in terms of the number of edges, but it's the weights, the total weights of the edges to be optimized. So if you look at this example, we have 9 vertices, right? So the total number of edges is the total number of minimum edges in the minimum spanning tree is 1, 2, 3, 4, 5, 6, 7, 8, which is 9 minus 1. So this is determined by mathematical rules. Okay, so after we laying out the definition, let's look at this particular example again. So if we sum up all the weights of this result of this example, we will find that the total weight is 37. And actually, this is not the unique minimum spanning tree. Okay, because basically we can remove the BC edge. Oops. Right, we can remove this edge, like remove this one and replace it with AH. Imagine that the AH is shaded now, right? And because the AH has the same weight as BC, and it also makes sure that all the vertices are connected. So this will result in a new tree that has the same minimum weights of total weights. So there could be more than one minimum spanning tree. This is another property of the problem. Okay. All right. So our task today is our goal today is to look at how a minimum spanning tree can be constructed or can be grown. Okay. And the way that we're looking into this problem is by first look at a generic method. Okay, so this is a generic method, or you can think of it as a template. It's not actual implementation of a solution, but it provides a general way of thinking in growing a MST, minimum spanning tree. Okay, and we will then introduce two concrete implementations, two concrete algorithms based on this generic method, based on with this generic way of thinking. The first one is called KRUSKAL, the second one is called Prims. And they use different data structures and a slightly different structure in choosing the candidates, in choosing the target edges for each iteration time. Okay. So the general method is a incremental algorithm in which one edge will be selected at a time, and the tree will be gradually grown, basically from empty to a complete tree. All right, so let's get started to look at this generic method. Okay. And the generic method is actually quite simple. It's just a pseudocode description of the algorithm. So it takes into two parameters, two arguments, the graph itself and the weight function. Okay, this is all the information we have. So it basically manages a set of edges. Okay, the capital A, which is initialized to empty, is a set of edges. This is the place, this is the variable that we store the results. Okay, because the results is a minimum spanning tree, and a minimum spanning tree is a set of edges. Okay, so and we will maintain the following loop variants in the weight loop, in this while loop. So before each iteration, A is a subset of some minimum spanning tree, some MST. We use some because the MST can be not unique, right? It can be, there could be multiple possible MSTs. So we just to make sure that A is just a subset of some minimal spanning tree. That's before each iteration. So what do we do in each iteration of the for loop here is that we will first find an edge, okay? And that edge should be safe for A, okay? And then we will add that edge from U to V to A using this union operation. Okay, so this union operation is a set operation. So this edge is safe. By safe, we mean that adding this edge to A should not violate the loop invariant. So after we add the edge to A should remain a subset of some minimal spanning tree. Okay, it should not violate this, and only in that way we will call the edge a safe edge. If adding that edge into the set will result in not a minimal spanning tree or not a subset of a minimal spanning tree, then we will not do that because this is not a safe edge. Okay, so this is quite a very conservative algorithm. Each time we only make a small step by including some edge that is safe to A. Okay, so and that's it. That's the basic general thoughts, the general algorithm, and it actually doesn't tell much about the details to us, because we don't know what a safe edge means, right? We don't know what could be a safe edge. So we will look at the slides to the next few slides to further give an operational definition to the concept of safe, because this is very important concept in order for us to come up with some concrete implementations, rather than this something as a pure concept in our mind. Okay. All right, let's come to the definition of the safe edges. This is a tricky part, and actually we need to lay out quite a few jargons, quite a few terms to define the safe edges. All right, we'll throw out a lot of the terms into the slides here. The first one is called cut. Okay. So a cut, as the name indicates, it is a action, or it is a split or a partition on the graph. Okay, and it's a partition on the vertices. As you can see here, it cuts the set of vertices into two partitions, two parts. The first part is S, and the second is the total vertex minus S, right? We basically cut all the vertices into two halves. So indicated by this graph here, you can think of the curve as a cut, okay? And we cut all the 9 vertices into two parts, two partitions. The black parts, the black vertices, they belong to the set S, and they are above the curve. And all the white vertices, they are under the curve, so they are in the second partition, V minus S. They are the white vertices. Okay. And then having a cut defined, then we can further define the cross and respect. And these are another two new verbs. Okay. So we say an edge from U to V crosses the cut if one of its endpoints is in S and the other is in V minus S. This is straightforward, right? Given a cut, so you can think of cut as a boundary. So if the edge crossed the boundary, one end is on S and the other is, the one end is connected to a black and the other end connects to a white vertices, then this is called cross. Okay. So in this example here, the edges, there are a lot of edges that cross the cuts here, from AH, right, BH, and where's BC, CD, DF, and EF. They all cross the edges, across the cuts. Okay, that's the so-called action of crossing. So, and now let's think of these subsets. So the subset A is a subset of the edges, okay, and they are shaded in the graph. So it's actually, let me use another color. This edge AB, IC, CF, GF, and HG. There are 5 edges, and it is the subset A. Okay, so given these subsets, we can define the concept of respect. We say that a cut respects a set A of edges if no edges in A cross the cut. Okay, so we use the verb cross to define the cross and the cut to define the verb, what respect mean. So in another language, if you think of this, all the shaded edges, none of them actually cross these cuts, right? When I do these cuts, I deliberately make sure that no edges in A are being crossed. So this is a cut that respects the set A of edges. So this is the third definition. And given these definitions, right, we define a lot, right? We define the cuts and the action of cross and the verb respect. Then we can use these notations to further define the notation of light edge. So we say that an edge is a light edge crossing a cut if its weight is the minimum among all the edges that cross the cut. Okay, so again, in this example, we already know that there are 6 edges that cross the cut, right? AH, BH, BC. And among these edges, if we consider their weights, then the edge CD has the minimum weight. Its weight is 7, right? It's a minimum number among 8, 11, 8, 14, and 10. Okay, so this one is the light edge that crossed the cuts. Okay, so the light edge actually can apply to other scenarios. It's not just can be applied to the edges that cross the cuts. Okay, and if there are more than one light edges, then we can, in most cases, we can randomly select one as the option. Okay, so more generally speaking, an edge can be a light edge with respect to any other properties other than the cross the cuts properties. But in this case, we'll consider the light edge that cross the cuts. Okay, all you need to, I think the most important thing is to remember the meaning, to use the original meaning of the word light. Okay, because it is light, so it must be the edge that has the minimal weights among all the edges that satisfy some properties. Okay, I think it's quite straightforward to memorize. Okay, so given all this bunch of notations, then we can use them to define the rules to find the safe edges. Okay, so again, let's go back to the generic minimum spanning tree algorithm pasted here. So the rule to recognize the safe edges can be given by the following theorem. Okay, it's quite a bit of text, but let's look at them, and it's quite, you will find that it actually makes sense. So given the graph G, right? Oops. Given the graph and the weight function W, so and A is a subset of the edges that include some minimum spanning tree. And now let's let the S and V minus S be a cut, okay, that respect A, okay, and let the edge be a light edge that crosses the cut. Then this theorem tells us that then the edge, the light edge, is exactly the safe edge that is needed to be included into A, or to be used to grow the subset A. Okay, so I hope that's clear. So let's repeat that again. Given a subset A, and we know that we assume that A is a subset of the minimum spanning trees. And because each time the algorithm tells us that before A becomes a minimum spanning tree, we need to take a safe edge, right? And as long as we choose the light edge, that crosses a cut. And this cut should respect A, which means this cut should not cross any existing edges in A. Then the light edge is exactly what we need to compute, to grow the tree. Okay, and let's look at how this theorem is proven. Okay, so oops. I will quickly go through this because this is quite, I think it's quite abstract, some concepts, but I think it will make sense if you, after the lecture, you go through the corresponding chapters in the several pages in the textbook. Okay. And when we prove this theorem, we will first assume that we will let T to be the minimum spanning tree that includes A, because our assumption is that the subset A is a subset of the minimum spanning tree. Okay, and also we need to assume that the T does not contain the light edge, right? Because if it does, then we are done with the proof. Okay, so we basically want to show some conflicts, or we want to like construct another minimum spanning tree T prime that includes the current subset A and the new safe edge from U to V. Okay, thereby we want to show, we can show that the U and V is a safe edge for A. Okay, because we want to construct a spanning tree, because that's the definition of the safe, right? If U and V is added to A and the result is still a subset of a minimum spanning tree, then we satisfy the definition of what a safe edge means. Okay, so let's further look at the proof. So because the tree T does not contain U and V, then the U V edge must form a cycle with the edge on the simple path from U to V in tree, because U and V is not contained in the tree, but the tree must reach all the vertices. That's what a minimum spanning tree means, right? Given a minimum spanning tree, it must connect all the vertices. But U and V is not included in the tree. So if U and V, so U and V must be reachable from each other through some other path, right? Because U and V, the edge itself is not included in the tree, but U and V are in the minimum spanning tree. So there must be another path indicated by the lowercase p here. Okay, so if we include U and V into the tree, then it will form a cycle, right? It will form a cycle in the tree. Okay, and then let's assume that since U and V are on opposite side of the cut, okay, we given that assumption in the theorem, and at least one edge in T lies on the simple path P and also cross the cuts. Okay, so we can imagine this because if there's a cut here, it crosses an edge, and we also know that there's already a cycle, then there must be another edge also across the cuts. Okay, and we assume that's edge to be xy, connecting from the vertex x to y. Okay, and that x and y edge is not in A because the cut respects the subset A. Okay, so we can remove xy, right? It basically breaks T into two components. Okay, and then we can add U and V to reconnect the two parts, and removing x and y, right? So basically what this proof does is that it's, okay, let me use the blue color. So the proof basically assumes that the original T actually includes these edges. So that's original T. So since x and y breaks the T, removing x and y will break the tree into two parts. Then we can remove x and y and reconnect the two parts with this u and v. Okay, and it will form a new minimum spanning tree, a new spanning tree with T prime. Okay, so now all we need to do is to show that T prime is also a minimum spanning tree, right? So basically, we want to show that the total weight summation of weights in T prime is the same as the original, as the old minimum spanning tree T. Okay, so at this current step, we will only know that T prime is a spanning tree, but we are yet to know that whether this is a minimum spanning tree or not. Okay, so next we want to show that T prime is indeed a minimum spanning tree. Okay, so this is quite easy since U and V is a light edge, right? A light edge means that it is the minimum tree. It is the minimum edge, which means the weight of U and V should be smaller than the weight of X and Y. Okay, and that means if we minusing X and Y first, and then plus something plus W plus the weight of U and V, the results should be smaller than or equal to the weight of tree, right? Because we minus is something that is greater, and then plus something that is smaller, then the results must be smaller than the weight of T tree, or the minimum spanning tree, right? But since T is already a minimum spanning tree, so we could not be strictly smaller than it. So the only possible results is that the weights of T prime equals the weights of T. Okay, and that says the resulting spanning tree like this is also a minimum spanning tree. And we are done with the proof. Basically, we show that U and V is safe for A. Adding U and V to A will create a minimum spanning tree. Okay, so this is a quite, I would say, abstract proof, and it could take a while to connect. But having this generic method in your mind, I think it will be helpful for you to understand the next two algorithms that we will introduce in a moment here. Okay. So let's look at the generic MST algorithm. So as the method proceeds, the set is always acyclic. Okay. So at any point, the graph is a forest. A forest means there could be different parts. So for example, here it is a forest that contains two trees, right? The three black vertices and the four white vertices, they are two trees. But eventually we're gonna shrink the size of the forest by connecting two components together, right? So there eventually the forest will merge into a one holistic tree. You can think of that each time we add an edge, safe edge, into A, it will connect distinct components in that is in the forest. Okay, and each time we add an edge, the number of trees in the forest can remain the same, or it can shrink by one. Okay, so the while loop will execute v minus 1 times. Okay, so do you still remember this quantity v minus 1? It is for sure, because if we want to connect all the vertices in the graph, then the number of edges must be the number of vertices minus 1, because this is a minimal spanning tree where we are constructing. So after this page, let's look at a concrete example here. Yeah, so the algorithm will end up with a single tree, and that is the point where the while loop will terminate. Okay. So we will introduce two algorithms, the Kruskal and the Prim's algorithm. Okay, and they both they work on top of the generic method, but they have different ways to define the cuts. Okay, and also they use a specific rule to determine the safe edge in the generic minimal spanning tree algorithm. Okay, so the definition or the rule for defining a safe edge actually depends on how the cut is defined, and how the cut is defined also depends on the type of data structures used. So, for example, in the Kruskal's algorithm, we will use a specific special type of algorithm called disjoint-set. Okay, so I think we will spend some time on looking at this disjoint-set data structure first. Say, it's a data structure that can be used to represent a forest of components. Okay, so the safe edge, if we use disjoint set, then the safe edge added to A is always a least weight edge that connects two distinct components. Okay, so we'll paste the Kruskal's algorithm here. So first, we will use a one for loop from line 2 to line 3, highlighted by the orange color, by the red color. So it actually iterates over all the vertices, and for each vertex, we will make it a set, or we initialize one vertex into a set. So in all, we create V trees or V sets, and we make each vertex a tree itself. Okay, and at line 4, we need to sort all the edges into an increasing or non-decreasing order by their weights. That is very important. Okay, we need to sort all the edges. Okay, and that sorted algorithms, sorted edges will be used in the next for loop, the second for loop, starting from line 5, which is a for loop that iterates over all the edges, but the iteration takes a non-decreasing order. Okay, we need to start from the least weighted edge. Okay, and iterates over all the edges in an increasing order. Okay, and in each step of the second for loop, we will basically use an if condition to examine whether the end points U and V belong to the same tree or belong to the same set. Right? Each time we iterate, in each iteration, we need to find an edge, and the two end points is U and V. So we will use an if statement to find the set for U and find the set for V, and we will check whether the set for U and V, they belong to the same set. If not, if they belong to the different sets, then we will merge the new edge into the set A. And then we will call union, which makes U and V into the same set. Okay. And finally, after all the edges are iterated over, then we will return A. Okay. In the second case of the if statements, if U and V they are already in the same sets, then we need to basically don't need to do anything because they are already in the one tree of the forest. Okay. So I think it will be easier if we go through a concrete example here. So some more background about disjoint sets. Okay. So disjoint set data structure maintains a collection of sets. So for example, we have a K sets, okay? And two sets are disjoints if they have no elements in common, okay? So there's no overlap, okay? So we will identify each set by a representative. So we use our elements in one set as a representative for the whole set, okay, which could be some member of the set. Okay, if you are interested, I would strongly recommend you to read the chapter 21 for more information about the disjoint sets. And I will paste some slides after this slide here. Yeah. So the basic operations on disjoint sets includes, first of all, the make sets, which are already used in the algorithm to initialize the vertex, right? So the make sets will create a new set whose only member and its representative is the element X. And the union, it will unite the sets that contains X and Y. Okay, so assume that the Sx is a set that contains X and Sy is a set that contains Y. Okay, so the union on X and Y will actually unite the two sets, not the two elements, but the two sets behind X and Y. Okay, so for example, if the Sx is xzw and Sy is ypq, so the union on X and Y will result in a new set that contains the 6 elements. Okay, that combines the two units together, the two sets together. All right, and the third function we use in the algorithm is find set. So it returns the representative of the unique set that contains X. Okay, so it basically tells that the current what the set for X is. So let's look at the example of applying a disjoint set to the graphs. Okay, we can use disjoint set to determine the connected components of an undirected graph. So these connected components may seem a different problem than the minimum spanning tree, but you will later find very close connections from the connected component to the Kruskal's algorithm. A lot of places in common. Okay, so this connected component is like this. If you recall Kruskal, you will see that you can already find a lot of overlaps here. First, we call make set on each vertex, right? This is what exactly the Kruskal's algorithm does. It makes each vertex its own set, initialized to its own set. And the second for loop, right? It's still the same second for loop. It iterates over all the edges, but this time no sorting, right? No sorting. We just iterates over all the edges, regardless of the order, regardless of the weights. And the if also looks similar, right? It judges whether the two for each edge, if the sets contain, if they are two different sets, then we will unite the two sets. Okay, if they are already in the same sets, then we need to do nothing. So if we run the algorithm, run the connected component algorithm on the graph, it will look like this. So this is the initial states of the graph. It contains 4 connected components, right? These are 4 are connected, and there's no edges between interconnected that interconnected all the components. So assume that we are going to run the connected component algorithm on this graph. Okay, so initially all the vertices are initialized to the sets, right, after line 1 to line 2. Then after the first iteration, you will see that the B and D are combined, right? B and D are initially 2 sets here, and after the first iteration of the line 3 for loop, they are combined. So this order is randomly selected because we don't have information about, well, we don't have information about which edge to go through in each iteration, right? But that doesn't matter. So all we need to know is that because B and D belongs to the 2 different sets, so the if condition will satisfy. So the results will be a union function of B and D, which will result in a new set B and D. Then after second iteration, E and G are united. After the next, A and C are united, and HI united, and ABCD united, and EFG united. Okay, and nothing changed. So that is the results of the connected components, and it can, as you can easily find, that it reflects the connected components in the original graph. So one connected component is stored into a set, right? A, B, C, D, they belong to one connected component, and the results is reflected in this set. They went into the same set. And the second component is also into a second set, third component, and the last component. So this is what the connected component does. And let's go back to the Kruskal's algorithm. We can see they are quite similar. If we highlight these parts, right, they are exactly the same. And the second part is almost the same, unless except for the parts that we need to sort all the edges by non-decreasing order, right, by their weights. And in the loop statement here, we also need to take the non-decreasing order by their weights. And another additional part is the initialization for the A, and each time we need to include the new edge into A. Okay, that's basically the difference. So another difference is that the minimum spanning tree algorithm, Kruskal's algorithm, assumes that the graph is connected. So there should be only one connected component after the MST-KRUSKAL's algorithm is done. Because in nature, it is just an algorithm that finds all the connected components. But we assume that for a connected graph, there's only one connected component. Okay, so that is our assumption before we run the minimum spanning tree. So if there are multiple components, then there shouldn't be a minimum spanning tree, right? A tree will not be able to span across all the vertices if there are some vertices that are not connected. All right, so now let's go through an example to see how Kruskal's algorithm runs. So we'll start from an empty A. So remember, A is the subset of minimal spanning tree that we grows incrementally. So, and all the vertices are initialized to trees or each to the smallest sets. Okay, so in the first iteration, because iteration makes sure that we will select the edges that have the we'll start from the least weighted edge, which is HG, that has the weight 1, right? So if we select HG or GH, because they initially belong to 2 sets, so the algorithm will merge them, right? And we'll first add that edge to A. So now A will contain 1 edge, and the resulting forest will be like this. So the GH will be merged into or united into one unit, one set. So that's after the first iteration. I will highlight the GH as it's part of the it's the current subsets A. And the second step, we'll look at the next minimum, the next smallest edge. So there are 2 options. It's IC or GH, and actually we can. It's also possible that we can go through GH, but this time the example shows that the IC will be selected. Okay, but it doesn't matter. So selecting IC will add IC into A. So now we have 2 edges, and also I and C will be merged into one set here. Okay. All right. Then the next smallest edge will be GH. GF. GF will be selected into A, and because now it's a special case because GH is already in one set and F is in its own set. So the resulting of merge G and H is a new set that has 3 elements, F, G, and H. They will be into one set. Okay, so that's after this step, we highlight the GH. And then we highlight A and B, right? A and B is done. Then we highlight C and F, right? C and F is done. Let's consider IG, okay? Because IG has the weight 6. Okay, but this time we will find that the if condition is not satisfied because the find set on I and the find set on G will return the same set. They are already in the same set, right? If you look at the example here, C, I, F, G, H, they are already in the same set. They are already connected. So there's no need to add this edge, IG, to the minimum spanning tree. Okay, it will cause a loop. It will cause a cycle. So IG is not added to A. So we'll need to consider the next candidates. Okay, what about CD? Yes, CD will be considered. CD is not C and D. They are in 2 sets, so they will be added into the minimum spanning tree. All right, and then then HI. When HI is considered, they don't belong to the same set, just like the IG in the previous slide, right? So HI will not be added to A. Okay, so the next one being considered is AH. Okay, AH will be considered. And then the sets will be merged. And BC will not be considered because they are already in the same sets. Okay. Lastly, we have DE. Okay, DE is considered. All right, now we'll consider the rest of the edges, and they will not be considered because all the elements, they are in the same tree. All the elements are in the same set. So the results is that we return A, and the A contains the edges of a minimum spanning tree, and A is exactly what we need because A connect all the edges in A connects to all the vertices in the graph, and the weight is minimized. because we select from the minimal from the least weighted edge, and we make sure that all the edges, they are sorted in a increasing or non-decreasing order. Okay. So if we analyze the running time a bit, it actually relies heavily on the efficiency of the disjoint data structure that we implement, because these make sets and find sets, union sets, they all need to cost us some running time, and the sorting edges will take that many time, right? Because if you take a very good sorting algorithm, it will be basically n times logarithm of n, right? And we have e many edges, that will be e times logarithm of e. And because the e is smaller than v squared, so we can also think of that logarithm of e is at the same level of logarithm of v. Okay. So from line to 8, we will need to perform, need to go through all the edges. So that will be big O of e times find set and union operations. Okay. And from line 2 to 3 here, it will be big O of v times of make set operations. And that put that in total, if we assume that the set operations will cost you alpha of v times, and the total cost will be big O of v plus e times alpha. And with a good implementation, the set can be a very slowly growing function. For example, bounded by the logarithm of the logarithm function. So in total, we can assume that the running time is big O of e times logarithm of b. Okay, so this is the results after assuming that probably the v and e, they are at the same level. So the algorithm, roughly speaking, the algorithm it runs almost at the same speed as the sorting algorithm. It's basically after you sort the algorithm, you just need to collect all the edges in the increasing weight order. So it's not a extremely slow algorithm. Depending, of course, it's the constant factors will be affected by the number of edges and number of vertices, but basically it's a quite efficient algorithm. So I think we'll stop here. We have analyzed, we have first proposed, introduced the general method for the minimum spanning tree problem. And I think it's worth to spending some time reading the chapter 21 about the, okay, it's not 21. 21 is about the disjoint set data structure. It's also worth reading. And the general algorithm actually paves the way for implementing Kruskal and the Prim's algorithm in the next time. We will talk about it. So the Kruskal algorithm actually relies on the disjoint sets, and the disjoint set algorithm, the disjoint set data structure supports the connect components algorithm. And you can see a lot of connections between the connected components algorithm and the Kruskal's algorithm. And I think I can release the homework today for graph algorithms so that you can start working on the problem sets. All right, and that's it for today.